we've been talking about power series, and more specifically Taylor series, and we're using these Taylor series to approximate functions that are not polynomials. So we take functions like the trig functions, or like the exponential function, or the logarithmic functions, and we write them as a polynomial. We write an approximation of them as a polynomial. So what I want to do real quick is talk about what it means for them to converge, because this is an important idea to know what it means to converge before we move on to figuring out when they actually do converge. So what we're going to do here is we're going to look at some series here, and the idea is a Taylor series converges at a particular x value. So I'm going to use sine as an example. Let's say I'm trying to figure out what the sine of 1 is. Okay, so 1 radian. I want to know what the sine is. If I don't have the capability of plugging sine of 1 into my calculator, one thing I might do is use the Taylor series for sine. 1 is fairly close to 0, so I could center it at 0 and just use the polynomial x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. What it means for the Taylor series for sine to converge is that if I use enough terms in that series, I'm going to get a number that is essentially the same. And if I use infinitely many, I'm going to get the sine of 1 by plugging it into that polynomial. So to converge means that the function itself and the Taylor series are the same thing with infinitely many terms. Now, we can't actually get infinitely many terms, so we're going to look at a limit. And we're going to say the limit as we add more and more terms, if the values of the Taylor series approach the values of the actual function, then it converges. If the values of the Taylor series do not approach the values of the function, then it doesn't converge. And what do we call it when it doesn't converge? It diverges. So to use the sine example, this is the first degree Taylor polynomial for sine. So we have the sine function, we have the first degree Taylor polynomial. I apologize for how small it is, but I'm going to put a bunch of graphs up here. So we'll see what happens as we add more and more terms. We can see that if we're at a number really close to 0, already the first order polynomial is pretty close. Because all the way up until about right here, and I'm going to just put brackets around it, they're essentially the same thing. They're on top of each other. But if we move far enough away from 0, then we get a pretty decent sized gap between the function and the approximation. And that gap is not ideal. As long as that gap's going to get smaller, then it's going to converge. So let's say that I'm trying to use this to approximate the value of the sine of pi. The sine of pi is right here at about 3.14, right? Well, would this be a good polynomial to approximate the sine of pi? No, because we can see the polynomial itself is off the graph up here at the top, so it would not be a good approximation. There's a large distance here between the function itself and the polynomial. So if I add another term, if I'm trying to approximate this at pi, you can see it stays closer to the function for a longer interval. So it's right on top of the function on that interval, but as we get further away, it gets farther. And it's hard to tell right now because this distance here doesn't look very big, but this is actually a worse approximation for pi right now than the first one was, but it's not very good either. But as we add more and more terms, we add the 5th term, now if we look at pi, this distance is getting a lot closer. Okay, that error is getting smaller and smaller. And as we add more and more terms, we can see that the Taylor polynomial is getting closer and closer to the sine function for a bigger and bigger interval. So where the interval here was, maybe from x going from -1/2 to +1/2, all the way down here to where we have the 17th order the polynomial is pretty much the same as sine all the way from about -7 to +7. And the more and more terms that we add, the more and more accuracy we get. And so what this means is on this interval here, we can tell that the polynomial is converging to sine after only about 17, after about the 17th order polynomial. Now, that's a big polynomial. That's x to the 17th power over 17 factorial. That's going to be the last term in it. What this indicates to me is that if I add enough terms, and it's going to have to be a lot, it's going to have to be infinitely many of them, but if I add enough, the interval is going to get bigger and bigger and bigger and bigger, and it's going to cover the entire x-axis. So this is converging, this polynomial is converging for all values of x. So this is the zero-order polynomial, Taylor polynomial for the function y equals 1 over 1 minus x. It's the zero order because it matches the behavior, just the value of the function, but it doesn't match any of the derivatives. If we match the first derivative, it's going to look like that, and that's just the tangent line approximation. And same thing, if we add more and more terms here, we can see that the approximation is getting better and better. So the first one, it really only gives us the value at the center itself, and that's it. The second one, we have an interval around the center that's not very big, but it gives us a pretty close approximation. If we get all the way to the fourth one, which is the third order polynomial, we get a bigger range here that we get a pretty good approximation. And if we go all the way to the 12th order, it actually looks a lot like the third order one. And what's happening here? This blue function is the Taylor polynomial, the 12th order Taylor polynomial. What's happening here? It's converging for some values, but not for others. Which values is it converging for? Which ones is it not? If we look at where it kind of cuts away here, this is getting really close to -1 as we go to the left. So to the right of this point right here, which is really, for this one, probably about 8/10 or -8/10, and then it peels away, and then it's completely different. It's very, very different at this point. And it doesn't matter how many terms I add, I'm never going to get an approximation that's going to tell me what 1 over 1 minus -2 is. I'm never going to get one that says that. And I'm also never going to get a polynomial that's going to all of a sudden jump down here and approximate this branch of the thing either. So what that tells me is it's only converging for some values. It's only converging when x is between -1 and +1. And so no matter how many terms I add, it's going to converge for these, but it's not going to converge for anything outside of that. And we saw why before. The Taylor polynomial that we use to approximate this is the geometric series 1 plus x squared plus x cubed plus and so on. And since this is a geometric series, x is the common ratio. The common ratio has to be less than 1 for it to converge. So if we wanted to approximate this function somewhere outside of that interval, we would have to center it somewhere else. We couldn't center it at 0 because we're not going to be able to get an approximation outside of our interval from -1 to 1.